Kaydı herhalde başlatmış olmam lazım hocam. Evet. Merhaba arkadaşlar. Mikro işlemciler laboratuvar dersine hoş geldiniz. Katılımınız için teşekkür ederim. Abbas hocam anlatacak. Ben de burada olacağım. Teşekkür ederim Abbas hocam. Buyurun.
Ben teşekkür ederim Muharrem hocam. Merhaba arkadaşlar. Her zaman yaptığımız gibi önce hızlıca bir geçen haftanın konusuna bakalım. Türkçe küçük bir tekrar niteliğinde. İşte compare'ımız vardı arkadaşlar, hatırlarsanız. Bu çıkarma işlemi yapıyordu. Birinci operanttan ikinci operantı çıkarıp sonucu kesinlikle bir yere yazmıyordu. Unutmayın. Sadece yaptığı bu çıkarma işlemine göre flag'leri değiştiriyordu. Biz bu flag değişimlerine göre bazı jump'lar kullanarak programın başka yerlerine atlamaya çalışıyorduk. Tabii bu CMP ile atlamak zorunda değilsiniz. Başka komutlar da flag'leri değiştirdiği için bu jump'ları başka komutlarla da kombin yaparak programın başka noktalarına atlayabiliyorduk. Assembly dilinin güzel tarafı programı satır satır işliyor olmasıydı. Prosedürel bir dil olmasıydı. Geçen haftanın konusu buydu. Bu haftanın konusu arkadaşlar daha kısa, daha basit bir konumuz var. Add with carry dediğimiz eldeli toplama, subtract with borrow dediğimiz işte yine eldeli çıkartma. İkisinde de kullanılan carry flag, tek bir flag'imiz kullanılıyor. İkisi de carry flag'e bakıyor. Önceden söylemiştim, hatırlarsanız borrow flag diye bir şey yok. O da carry flag. Böyle arkadaşlar. İngilizceye geçmeme müsaade edin lütfen. Okay, my friends, today's topics are add with carry and subtract with borrow. This topic is a bit important but easy because it's only look for the carry flag and make an addition operation. According to carry flag, addition operation will be 1 plus or minus 1. It depends on the situation. For example, let me first open the add with carry help. Remember, we always go to instruction set first for a new instruction. Add with carry ADC is add with carry. Algorithm is operand 1, operand 1 is equal to operand 1 and operand 2 plus carry flag. It adds the carry flag into addition. For example, if carry flag is 0, this is a simple add operation. If carry flag is 1, this is add with carry. Types, parameter types, register memory, memory register, register register, memory immediate, register immediate. This is typical parameters. It can affect all the flags, and here is the simple example. Example, there's a new instruction, STC. STC means set carry. Set carry flag. It sets the carry flag to the 1. It affects the carry flag. There's no operand. There's only instruction. Okay, let me emulate this code and see the flags also. Look at the carry flag. With this STC command instruction, we set the carry flag directly, so that we know that carry flag is 1 now. We put 5 in AL and we make an add with carry operation. 5 plus 1 plus 1, which is 7 into AL. As you can see, AL becomes 7. This is register immediate combination of these parameters, register immediate parameter. It can be different versions. I'll move directly into, let me remove this set with carry and emulate again and see there's no difference between add and add with carry if the carry flag is 0. For example, look at the flags. We didn't set flags. We put 5 in AL and we are going to add 5 plus 1, which will result into 6. because carry flag is 0. Carry flag is 0. The result is 6. Or in this case, ADC is equal to ADD because carry flag is 0. Okay. Now I'm going over to next instruction, which is subtract with borrow. Subtract with borrow. Borrow, there's no borrow flag. I'm repeating this statement again and again. It is also carry flag. Operation is operand 1 minus operand 2 minus carry flag. Register parameter types are same, register, memory, register, etc. And here is an example again, a simple example. We set the carry flag, this set carry flag to 1. Put 5 in AL and subtract with borrow. Remember the algorithm. It makes the subtract operation 5 minus 3, which is 2, and again subtract the carry flag from it, which is, as you can see from here, which is 1. Let's emulate this one. Okay, we set the carry flag back and forth. Put 5 in AL and make subtract operation by looking at the carry flag. There is an important catch in here. Please look at the carry flag after subtract with borrow operation. Carry flag is updated, cleared. As we can see, after subtract operation, carry flag is cleared. It was same with ADC. ADC also clears the carry flag. For example, there's an 5 plus 3 plus 1, which is 9. After ADC operation, carry flag is also 0, cleared, whatever you call it. Okay, this is two instructions, the easy two instructions. The catch, the hard part of these instructions are in the example parts. Examples are a bit hard in this topic. We are going to work with 4-byte integers. 4-byte integers mean 32 bits. Remember, oops. 1 byte means 8 bit. 4 byte means 82 bit. Why it is important? Why there is a question about 4-byte integers? Let me read the question first. Write a program that adds two 4-byte integers written on 1008 and 1004 H address and put result into 1008 address. First integer is 3 billion. Second integer is 1 billion. Okay. I'm going to write this simple add operation. For example, I'm going to move AX 3 billion decimal, and I'm going to put 1 billion decimal and make an add operation to result in AX, and I'm going to move this into something 1008. Okay, so is this possible? 3 billion plus 1 billion. This operation can be handled by 8086 architecture. It's actually no. Cannot be evaluated. Let me zoom in here. Cannot be evaluated 3 billion undefined variable or over 16 bits. Says the number 3 billion is over 16 bits. Let me open a calculator and see the hexadecimal version of 3 billion. Okay, this is 3 billion. As you can see, hex version is, let me write it down in here with a comma, B2D05E00. As we can see, every character in hexadecimal is 4-bit, 6-bit, 12-bit, 16-bit, 16-bit, 16-bit, 32-bit. So 3 billion only fits into 32-bit memory or 32-bit register. But our emulator, which is 16-bit architecture, does not support 32-bit register. That's why we have to find a way to add these two numbers. Okay, question is this. You have to find a way. Let me, by the way, write the 1 billion also. What is the 1 billion in hexadecimal? 3B 9A CA00. Okay, this is 3 billion. Let me add this and see the 4 billion. Okay, 4 billion is EE6B 2800. Okay, this is 4 billion. This is 1 billion. This is 3 billion. Okay, let's get rid of this calculator. Okay, how we are going to do that? We have only 16-bit registers, but these numbers are 32 bits. Normally, if this lesson is in our lab, I expect answers from you, but today I'm not expecting an answer from you, but Salah has an idea. The carry flag is automatically set to 1 when there is a carry white addition progress. I don't understand the question, but it's not about our my question. Salah, could you please ask that question after the lesson? At the end of the lesson, I will explain that, if I understand it. Okay, we have 3 billion and 1 billion. We are going to add these two numbers. We have addition here. Let's say like this. We have an addition operation. 0 plus 0 is 0. 0 plus 0 is 0. E plus A is 8. Let's open this calculator again and calculate this hexadecimal operation. E plus A, which is 1/8. 8 is written down in here. 8 is written down in here. We have 1 carry. Okay, now I'm going to add this 5 plus C. 5 plus C is 1, 1. But we have also carry, so I'm going to add 1, which will become 1, 2. So 2 is here. We have carry in here. We have carry in here. So I'm going to calculate 0 plus A. 0 plus A is A. A plus carry, which is 1, becomes B. After that, D plus 9. D plus 9, which is 1, 6. 6 is written down here. We have a carry in here. B plus 2 is C, D, D. We have a carry, so it will be E. There's no carry in here. B plus 3 is, as you can see, it is E. So addition operation is this. This is 3 billion, this is 1 billion, this is 4 billion. We can add 16-bit part of these numbers into registers. Let's open the example in here. By the way, I want to see your text in here. I'm going to put the lower part of this 3 billion into, for example, AX, which is 5E00, and upper part of 3 billion into BX, B2, D0. By the way, these are hexadecimal. And put lower part of 1 billion into CX and upper part of 1 billion into DX. 3B, 9A. These are hexadecimal. If there is an alphanumerical character, we have to put a 0 beforehand. Okay. So the first part, we are going to add these two registers, which are AX plus CX. Add operation, AX plus CX. The result will be in AX. And the second part, which will be BX plus DX. Add operation, BX plus DX. The result will be in BX. So the result will be in BX AX combine. Okay. Let's emulate this code and see if it is correct. What was the result? Result is EE6B. Let me put this in here. Okay. We put lower part in AX, higher boundary in BX. So 3 billion is in BX AX combination. Okay. So BX AX is 3 billion if you combine them in your mind. Okay, actually they are not 3 billion. Okay, I put lower part in CX, higher part in DX, and 1 billion becomes DX CX combination. Okay, so add operations. We add the lower parts AX plus CX, and the result is 2800. As you can see, the lower part of the result is correct, and the upper part is calculated, and the result is EE6A. The result is not correct, because between these operations there was a carry which was calculated between these two addition operations. So we have to put this carry into second operation. Okay, let me open the flex for you and see the flex while we make this additions operation. Okay, we put lower part into. Do I have to see this? Lower part into AX, upper part into BX, lower part into CX, upper part into DX. Okay, addition operation, first addition operation, which was the lower parts addition operation, as you can see, set the carry flag. The flag is now 1. Now, if I change this second code with add with carry, it will include the carry flag into this addition operation. Second part will be adding this, and this. So the result will be correct. I'm going to emulate this. Go one by one till addition operation. Open the flags. First, lower boundary is calculated. See, carry flag is 1. Now the upper boundary is upper 16-bit calculated. And the result is, as you can see, EE6B. The result is correct. So the 4 billion is stored into BX AX combination. This is 4 billion. This is 1 billion. Okay. Is there any question? Yes, Mehmet, you are right. The topic is add with carry. We have to use add with carry. Is there any question about the concept? But be careful. For example, after this operation is done, BX is, for example, what? Octal hexadecimal EE6B. Unsigned number of BX is 61,000. EX is 10,000. 10,000 plus 61,000 is not 3 billion. Why we did not use EAX? EAX is in X86. We doesn't have an EAX in 8086. X86, X86, which is 32-bit architecture, has EAX. It doesn't have EAX. Okay, Salah? That's actually the question is that 8086 architecture is 16-bit architecture. X86 architecture is 32-bit architecture and also supports 64-bit architecture. It doesn't have EAX. As you can see, when we emulate in here, all the registers are here. There is no EAX. Okay? Any other question? By the way, the answer is not this. The question states that the number is here and you should put the result in here. So we need to update the question. So let's put this into 1000H and the upper boundary is into 1002H. 1000, 1001, 1002, 1003. One 1004H and 1006H. Okay, we put this value in the memory. Let's emulate those 4 lines. I'm going to go over and look at the memory. As you can see, B2D05E00. This 4 line states the 3 billion. This 4 line states the 1 billion. Okay. Let me zoom in and show you the line in here. The upper bound of this here is 3 billion. The lower boundaries of this here is 1 billion. Question saying that, where is the question? Question is here. Question saying that first number starts from 1000H, the second number starts from 1004H, and it wants the result should be into 1008H. Okay, we should update this addition operation. But remember, there is no memory to memory operand. That's why we have to put one of those address into register. For example, AX. Putting 1000H into AX, or it doesn't matter. We then update this one. Oh, this is AX. Okay, CX is 1002. The resulting AX. Okay, now we need to put one of these. Oh, this is wrong. The lower parts will be added. So this is 1004. We need to put dx from value. Dx will be, what will be the, we put this into AX and make addition operation with 1004. So we put this into BX, make addition operation with 1006. Okay. Later we have to put the result into 1000H, the lower parts, which will be in AX, and the upper part, which will be in 1000 and AH, will be in BX. Be careful, adding 2 into 1008 doesn't equal to 1010. It is equal to 1010A. Okay, let's see if we make things correct. Emulate, emulate, emulate, emulate. At the end of this question, let's go and look at the result. EE6B2800. Yes, the result is stored correctly. Any question now? We know that these two memory combination stores the half of these numbers in hexadecimal form. For example, half of 1 billion doesn't equal to 500 million. The combination of these two hexadecimal is equal to 1 billion. Okay? Second question. If there isn't any question, I'm going over second examples. There is no question. Okay. Let's go and look at the second example. Write a program that subtracts two 4-byte size unsigned integers. The first question is addition. The second question is subtraction, which is we are going to use subtract with borrow. But there's a catch. Remember this operation. We start addition from the least significant bit. Okay? In normal subtract operation, we as a human make the subtract operation start from here. But in order to calculate the carry, we start the subtract operation from here. Am I right? I couldn't be sure, but let's see. Let's try. It's not that easy to try. But first, let's calculate the 2 billion. Because 3 billion minus 1 billion is 2 billion. Which is 7735. 7735. 9400, which is 2 billion. Okay, we have 3 billion in this address, 1 billion in this address. These are same. Now we are going to make the subtract operation. Okay, we are going to make, let's change directly this into subtract and subtract with borrow and see if it is correct or not. I'm not 100% sure. That's why I'm going to try. Okay, emulate, go one by one. And let's go over and look at the result. Result is 7735, 9400. Yeah, it works. So just forget about what I said. As a human, we start from here, but for now, we should start here. That was incorrect. We make the subtract operation in here. 0 minus 0 is 0. 0 minus 0 is 0. E minus A. Let's make this operation. E minus A is 4. 4 is written down in here. I'm going to delete these lines. 5 minus C. 5 minus C is equal to FFF9. So we put 9 in here, and we have a carry. F means minus, remember. We have carry, so I'm going to subtract 0 minus A, 0 minus A, minus carry, which is 1. The result will be 5. Again, there's a carry. D minus 9 is 4, minus 1 is 3. 2 minus B is equal 7, but we have a carry. B minus 3 is 8, but we have a carry, so that's why we have 7 in here. The carry operation between these 16 bits is handled by the architecture, but the carry between these two 16 bits is handled by us with the help of carry flag and add with carry operation. Okay? So the result is 7735, 9400. Okay, any question about the subtract and subtract with borrow? We use subtract first because there's no carry between beforehand. It doesn't have a carry. If the carry is clear, we can directly also use subtract with borrow, but we can't be sure beforehand there may be carry. So in order to make sure it doesn't put carry into calculation, we use subtract, or we can set carry or clear carry. There should be an instruction which clears carry. What was the name of clear carry? CLC, yeah, clear carry flag. Okay, let's first use clear carry flag so that this subtract operation does not work with carry. We can use subtract with borrow in here because we have already cleared carry. This is also true. But in order to make sure, subtract and subtract with borrow combination is more true. Okay, third question. Write a program that compares two 4-byte size unsigned integers written on 1000H and 1004H address, and if integer that's written on 1000H address is bigger than other, then subtract two numbers. If the first number is bigger than second number, subtract. If not, add. Okay, so there is a single if-else. This if-else looks for the first number. If the first number is bigger than second number, it will make a subtract operation. If it is not bigger, it will make a addition operation. Okay, so the numbers now is 4 billion and 2 billion. Why we did change the numbers? I'm not going to change the numbers for now. 3 billion and 1 billion is okay for me. So this is 3 billion, this is 1 billion. I'm going to compare these two numbers. How can I compare these two numbers? With compare instruction, I can only compare 16 bits, maximum 16-bit values. I can compare the lower parts, I can compare the higher parts. How can you understand a number is bigger than something other? For example, we have A, we have B. How did you compare A is bigger than B? Do you have an idea? How do you compare a number is bigger than other number? An idea? Bx minus dx. It says the higher part of the most left side and going left. I think by subtraction and flex. Okay, compare operation already making subtraction, but compare operation only makes subtraction with 16-bit. But these numbers are 32-bit. So Utku and Ömer is right. We have to start from the most significant bit, most significant part of the numbers. Let's forget about the hexadecimal part and, for example, 1, 2, 3, 1 million goes like that. And we have another number, 1,000,007, and goes like this. How did you understand that the first number is bigger than second number? We simply make a subtract operation and look at the result. If the result is bigger than 0, the first element is bigger than second element. If the result is smaller than 0, if the result is negative number, so the second element is bigger. But we cannot directly make subtraction with 32 bits. That's why we have to calculate the most significant part of this 32 bits and look at the result. Since these are 32 bits, we know that these numbers have upper part of 16 bits. Let's go over and look at the numbers. For example, if these numbers are like this, is this 32-bit number? No, this is only 16-bit number with zeros beforehand. So we know that these numbers have higher boundaries of 16-bit. And we should compare the higher boundaries of this 16-bit as Utku and Ömer says. So I'm going to compare Bx with Dx, the higher boundaries of these numbers. This operation is going to set some flags. Okay, let's go over and look at the flags. We put the values into there and compare operation. We compare numbers. 0 flag is set to 1, stating that the result is 0. Why? Because we doesn't have Bx and Dx in. Yeah, Ömer, you are right. We didn't put Bx into something or Dx into something. You have to be careful. Upper boundary is 1002H. And let's say upper boundaries is, let's look at the compare instruction. If it does memory to memory compare, we may use directly, but it doesn't have a memory to memory. Damn. So that's why we are going to use registers. Now we have compare operation. We put these values into bx and dx. Bx as b2, d0, dx as 3b9a. We are going to compare and open the flags. Compare operation, set some flags. According to those flags, I'm going to do some operation. Now, I'm looking for if the first operand is greater than second operand. That's why I'm going to use a jump, which is jump above or jump grade. I need to use one of these. The only difference between these instructions is one of them is signed, the other is unsigned. So I'm going back and looking at the question. If the numbers are signed or unsigned. Question states that these numbers are unsigned integer numbers. That's why I'm going to use jump above. After this operation, I'm going to jump above. Greater. Part, we have greater in here. The smaller is here. When we jump into here, we make the subtract operation in here. Oh, I delete the subtract code. I shouldn't have deleted that code. Delete operation. If smaller, addition operation. But after these smaller things, I have to jump and unconditional jump and okay, this is if as part. If greater, it jumps. This is the if part. This is the else part. If greater is, if the first number is greater than second number, it will jump to greater and make a delete operation and will end. If the first operand is not greater than second operand, it doesn't jump and it will make the addition operation and jump to end. That is the answer. The inner part of this addition and deletion operations are actually the first and the second question. Remember, first question was addition operation, second question was subtract operation. That's why I'm going to open the answers and copy paste the results. Don't do that. Where was that? Oh, it is in my site. It was in content, laboratory, microprocessors, codes. This is the fourth week, first and second question. Okay, these are the answers of first and second question. Let me show you the answer. It has numbers in. It used bx as a 1000H address, bx plus 2, 1002, bx plus 4. It used base pointer, base register, bx. This is exactly the same thing. It adds, this is subtract, second question. Yes, this is subtract. I'm going to copy this subtract from here. From here. Where is the subtract operation? Subtract is here. Paste the subtract in here. but we have to make corrections. Let me give an indentation in here. What was the subtract we was using? We were using, it was for 1004 minus 1000. We were using 1000, 1002, 1004, 1006. We have to make subtraction operation 1010, 1004. So it doesn't have an AX or BX. Let's put AX and CX again. Okay, now I'm going to subtract AX minus CX. And again subtract AX minus CX, BX minus DX. Result will be in BX AX combination. So addition is only add AX CX, add with carry BX DX. Okay. I think this is correct. Let's emulate and see if it's calculating correctly. For example, in here, 3 billion is greater than 1 billion. That's why it's going to make a subtract operation. Let's check from here. We put the values into memory, gather them back into AX, BX, CX, DX, make a compare operation, open the flex. After compare operation, some flex have set it. Jump above. If greater, it will jump. So it jumps into greater part, which is subtract part. It's going to make a subtract operation, and the result is in BX-AX combination 77, 35, 94, 00, which was 77, 35, 94, 00. This was subtract operation, remember. Let's change the numbers with 1 billion, 3 billion, vice versa. How can I change that? I can put this into here and put this into here. Into here, put this into here. I changed them. Now emulate again. Open the flex again. Put the values AX, BX, CX, DX. Compare operation. Now compare operation set some other flex. For example, carry flag is set, sign flag is set, the result is negative. So it will not jump and dive into smaller part. So it makes addition operation and the result is EE. The result should be, oh, the result is wrong. BX, DX. What was the result of 3 billion plus 1 billion. Decimal 4 billion. 4 billion is EE 6B2800. It was wrong. So we make something wrong. We change the numbers. We compare the higher boundaries. 3B9A. Oh, we mess up. We didn't change the number correctly. We messed things up. For example, this is the lower boundary of 3 billion. Let me raise this all. This should be the lower boundaries of the first number, lower boundaries of the second number, and higher boundaries of the first number, higher boundaries of the second number. Oops, higher boundaries of the first number, higher boundaries of the second number. Yes. 0, H, 0. Oops, we put them in the wrong section. Should be in the here. Benden dikkatlisiniz vallahi arkadaşlar. Tebrik ederim. Evet. By this way, this will be into smaller parts. Yeah. The result will be things mess up very badly again. What's the wrong? 1000 and 1002. This is the second number. Oh, I couldn't find the correct way. Sorry. This is the second number. This is the first number. Finally. Sorry. They are in the smaller part, and the result is yes, this is the correct way. Finally, we get the answers. Yok bu doğru. Yani ilk sayımızı bu ikisinde, ikinci sayımızı bu ikisinde gösteriyoruz. Ben karıştırdım. Zaten bunun cevaplarını paylaşacağım. Buna birebir aynı olmayabilir de o da doğru. İlk sayımız, ikinci sayımız. Hani ikisini yerini değiştirmemiz gerektiğinde bunları ikisini de getirmemiz lazımdı. Karıştırdık. Ama önemli olan çıkarma işlemini neyle yapacağımız. Hayır, o yüksek taraf. İlk 16 bitlik kısmı çıkarmanız gerekiyor. Çünkü biz 16 bitlik çıkarma yapabiliyoruz. Gibi. Okay. Is there any question about carry flag, bigger numbers, 8086 architecture, 16-bit architecture, 32-bit architecture? Is there any question? There's no question, I think.
Tekrar merhaba arkadaşlar.
Arkadaşların sorusu da yokmuş hocam.
Tamam,
Kaydı burada sonlandırabiliriz.
Tamam, katılımınız için teşekkür ederim arkadaşlar. Abbas hocam teşekkür ederim. Dillerinize sağlık.
Rica ederim hocam.
Sağlık. Hoşça kalın hocam. Hoşça kalın arkadaşlar.